Hello everyone. Today we're going to talk about relative extrema. Relative extrema is really just talking about relative extremes. And the relative extremes that we are going to talk about in math are relative maximums and relative minimums. Okay, so I have the definitions down for relative maximum and minimum, and I'd ask that you'd write those down and get them copied into your notes. A relative maximum is a point whose value must be greater than the value to the left and to the right. And a relative minimum is a point whose value must be less than the value to the left and to the right. So I think that you talked a little bit about this last year in pre-calculus. Just want to review it with you. Okay, if we have some different points here, I'm going to go ahead and name them A, B, C, D, E. Okay, so as we look at this, and I'm actually going to, just for conversation's sake, I'm going to turn, and I'd ask that you kind of make a version of this graph here for yourself in your notes. I'm going to turn that arrow into an endpoint just so we have that to talk about as well. Okay, so if I start with point A and I take a look at it and I say, point A, is that point greater than or less than the point to the left and to the right of it? And you can see that, hopefully, you recognize that it is in fact greater than. So point A is our first relative max. Okay, let's move on to point B. And we recognize that point B here, okay, is that now greater than, larger than, the values to the left and to the right, or is it smaller than? And hopefully this time you recognize that this is a relative min. Okay, as we look through the graph, we can hopefully recognize our other relative maximums as point C and point E. And our last point, or D, is our last relative minimum. All right, now what about this point F that I wanted us to talk about? So notice the definition talks about has to be greater than or less than the value to the left and to the right. So if we look at F, we could definitely say it's less than the values to the left of it, but we don't have any values to the right of it. And so therefore, we cannot call it a relative min or max. Okay, so I just want to review intervals of increase and decrease and talk about how that affects the derivative of the graph. So as we look at these, and again, hopefully this should be a review from pre-calc last year, we can see that this graph is increasing. Okay, we're always looking, I should have said this first, we're always looking at this when we talk about this from left to right. So we always want to move from left to right on the graph. Okay, so if we look at this first one, we can see that as I move from left to right, I'm first going up, and then I go down. So we would say that it would be increasing over the interval negative infinity up until an x value of -1. And if you remember, we always use parentheses with infinity. And then we also use parentheses at the -1. And the reason why is because at -1 here, we would say it's increasing up until we get to -1, and then it begins to decrease. So at -1, it's neither increasing or decreasing. It's reached its relative maximum. And so we use a parenthesis so as to not include that -1 in our interval. Okay, then we would go ahead and say it's decreasing from -1 to infinity. All right, now what about f prime of x? What do we know about that? Well, first of all, f prime of x at x equals -1. Okay, so at our relative max here. Well, because when we look at this relative maximum, we can recognize that we will have the slope, which is what f prime of x is going to be a horizontal line, is going to be a horizontal tangent. We know that f prime of x is equal to 0 for this one. Okay, looking at our second one, all right, this graph has a unique shape to it, and this is actually called a cusp when it kind of is inverted like that. And then comes up to this point and then swings back down. So again, though, I can still discuss intervals of increasing and decreasing. As I move from left to right, I first am increasing until I reach that cusp, and then I decrease. And so my interval of increase would be negative infinity up until an x value of 3, again using parentheses. And then I would decrease from 3 to infinity. Okay, now what can we say about the derivative of f prime of x at x equals 3? Well, hopefully you would recognize that you can't draw a horizontal tangent here. In fact, if we try to draw in a tangent, we'll see is that we have actually values that kind of end up like teetering on that point. And so we're not able to draw it. Therefore, that tells us that the derivative at x equals 3 does not exist. Okay. All right, let's look at our third example here. This time we have a upward facing parabola, and so as I move from left to right, we can see that we first are going down and then we turn around and come back up. So we can see that we start with going down, so we're starting with the decreasing. So I'm going to say that we decrease from negative infinity up until an x value of 2. And then we increase from 2 to infinity. Okay, and again, this is just like the one above it. We will have a horizontal tangent at the x value of 2. So at x equals 2, we can say that f prime of x is going to equal 0. Okay, last one is an absolute value graph. Again, interval of increase would be where the graph is going up from left to right. So the interval of increase here would be from -5 to infinity. The interval of decrease would be where the graph is going down. So that's from negative infinity up until -5. And what can we say about the derivative of f at x equals -5? Well, now this one we come to a point. So once again, I'm not going to be able to draw in a vertical tangent. Okay, when I come to a sharp corner, okay, a 90-degree angle or a point like that. Instead, we have to say that it does not exist. Okay, critical numbers are defined as x values where the derivative of the function is 0 or undefined, since these are the places that the relative local extrema occur. So we just saw in those 4 examples, when we had a derivative of the function that was 0, then we would have a horizontal tangent and we would have either a relative min or a relative max. Also, where we saw the derivative of the function being undefined. Now, it has to be undefined and it also has to be a continuous at that value. So if it's continuous and the derivative is undefined there, then these are the places where you have a relative min or a relative max, as in the examples, like I said, that we just went through. Make sure you get that definition down in your notebook. Okay, it's very important and we're going to use it a lot the next several days. So this is super important that we know what critical values are and that we're able to find them. All right, so we're going to go ahead and just find the critical values for these first 2 examples. So it's talking about where the derivative is 0 or undefined. So definitely we want to go right ahead and find the derivative of this function. So that would be 3x squared plus 2x minus 1. All right, so now we want to go ahead and set that. This is a polynomial function, so we're not really going to worry about the undefined piece here. We're just going to go ahead and set that equal to 0. 3x squared plus 2x minus 1. Okay, it's a quadratic, so I should be looking at what are the factors here. So I know I have 3x and x, and I know I'm going to have 1 and 1 in order to multiply this to the 3x squared in the front and the 1 in the back. Okay, so now we just have to kind of test if we're going to have a plus or a minus in the middles here. So I know my outside 3x times 1 would be 3x, and my inside 1 times x would be x. So I would want the 3x to be positive, so I'm going to put my plus sign there, and the 1x to be negative, so I'm going to put my minus here. All right, so now that I have that factored, I can go ahead and do my t-charts, and I get x to be 1/3 here, add the 1 divided by 3, and x to equal -1. So those are my 2 critical values for that first function. Okay, the second one is a little bit more involved. We have f of x equaling x squared plus 4 all over x. So again, we need to do the derivative. Well, hopefully you recognize that the denominator here, we don't need to use the quotient rule because our denominator is simply a monomial. So when we have a monomial, we want to go ahead and divide that into both pieces. We want to break up the top. So we'd have x squared divided by x, which would be x. And then we'd also have 4 divided by x, which I would want to rewrite as 4x to the -1. Okay, so now I'm ready to take the derivative of that. Derivative of x is simply 1, and then minus 4x to the negative 2. Okay, so let's clean this up. F prime of x is equal to 1 minus 4 over x squared. Okay, I'm going to want to go ahead and get a common denominator. So clearly my denominator was going to be, my least common denominator is going to be x squared here. So I'm going to change this 1 into x squared over x squared. So then that would make my f prime of x equal to x squared minus 4 in the numerator over x squared in the denominator. Okay, so this is not a polynomial function. This is a rational function. So when I have a rational function like this, I have to think about two different scenarios, okay? Where is that derivative going to be 0 and where is it going to be undefined? Well, what that means is if the derivative here, if this were going to equal 0, then that means the numerator would have to equal 0. So I have to set my numerator equal to 0 to find the zeros. If it's going to be undefined, it means the denominator is going to equal 0. So I have to set my denominator equal to 0 to find my undefined values. Okay, so we're going to go ahead and do that. Okay, so I'm going to go ahead and find my zeros and also find my undefined values. So my zeros would be where the numerator, x squared minus 4, equals 0. So that would be x squared equals 4. So x is going to equal positive, and don't forget your negative 2. Okay, then you're going to set your denominator equal to 0 to find your undefined value. So that's just going to be x equals 0. So we have 3 critical values. 2 come from the zeros, and 1 comes from where the derivative is undefined. Okay, the next thing we're going to talk about is something called the first derivative test. And this is just such important stuff. And we're going to use this test throughout the course of the year in many different applications. So I want you to, again, get all these notes down. Make sure you have them all correctly written in your notebook. And I'm just going to start talking through them. So the first thing it says is, for a first derivative test, this is how you perform it. These are your 4 steps that we're going to go through. First, you're going to find all critical points. So we've just done that. I practiced how to do that. Okay. Second, you're going to create a sign chart that is labeled, and we'll talk about how to do that. Third, you're going to test the values in f prime of x. So we want to underline that you definitely are going to be using the testing. You're going to be testing those in the derivative function. Then we're going to go ahead and state our conclusions. And this is where our conclusions are going to come from in these next several bullets. So when we're asked to do this, questions like this, we're going to be asked to find the intervals of increase and decrease using the first derivative test. So what we need to understand is that intervals in which f prime of x is greater than 0, in other words, where the derivative is positive, indicate that the function, the original function, was increasing. Okay, this should make sense to us. All right, we just talked about, all right, intervals of increase and decrease. So you can see here in this example, when I am going up, okay, what do I know about my slope of my graph for this portion where f of x is increasing? I know that my slope is positive, and that's what this is saying. All right, intervals in which f prime of x are less than 0, in other words, negative, indicate that it's decreasing. So if I take a look at where this graph that and we'll call this f of x, if this was decreasing, where is it decreasing? Well, it's where the slope is negative. Okay, finding relative maximums and minimums. So then once we have this, once we understand where we're increasing and where we're decreasing, well, then we can understand where we have relative maxes and mins. So what this is saying is if my f prime changes from positive to negative, so if it changes from positive, which when we said it was positive, then it was an increasing function. Okay, so if it changes from positive to negative, then what happens is we have a relative maximum. If f prime of x changes from negative, in other words, a downward facing, to positive, okay, then we're going to have a relative minimum. So when our slope changes from positive to negative, as in this example here, positive to negative, we have a relative max. If our slope changes from negative to positive, we have a relative min. Okay, so let's start tying this all together. We're going to practice a bunch of examples. All right, so we're going to state the relative extrema in all intervals where f of x is increasing and decreasing. So remember, relative extrema are just relative maxes and mins, and then the intervals where the function, the original function, is increasing and decreasing. Okay, so we're going to start with, like I said, a really straightforward one. F of x equals x squared minus 6x plus 8. Okay, so if I want to know about this, the first step, if you go back to those four steps, the first step was to find the critical values. And we talked about how to do that. We are going to set the derivative equal to 0 or the undefined. So we have 2x minus 6. All right, so very easy. If I set that equal to 0, I'd have 6 is equal to 2x, so x would be 3. That's our critical value. Okay, that's our critical value. Second step was to test it on a number line and make sure that you label. So what the heck is that all about? Well, this is super important, like I said. Okay, so we're going to go ahead and draw ourselves a number line. And on that number line, we're going to put our critical value. Okay, and because this critical value came from a 0, where the derivative was equal to 0, we can label it with a 0 up above it. Okay, now this is where some of the labels are really important. We always want to understand that this was talking about f, and up here is going to talk about f prime. Always want to put those labels. The bottom is talking about f, the top is talking about f prime. Okay, so that's going to help us understand the behavior of both the original function and the derivative. All right, so next, we need to go ahead and test values into f prime of x. What does that mean? What's that all about? All right, well, what we want to do is test values to the left and to the right of our critical value. So we could test a value, anything that is smaller than 3, so we could test like a 0, and anything that is greater than 3, so we could test like a 4. Okay, so we're going to plug those values into f prime of x, and we're going to determine if we end up with a positive or a negative. The value that we get does not matter. What matters is if it is a positive or a negative number. So when I plug 0 into f prime of x, all right, I would have 2 times 0 minus 6. What do I get? Well, 2 times 0 is 0, minus 6 is going to be a negative value. So notice I put that with f prime because I plugged it into f prime. All right, now 4, okay, plug that in. I get 2 times 4 is 8 minus 6. That's going to be a positive value. All right, and you don't actually have to do all this writing down here. It's just all this down here. It's not really necessary. I'm just showing you what I'm doing. All right, so because we have an f prime that is negative, what does that mean about f? Well, that means that f is going down. Okay, so we're going to put an arrow pointing down, that it's decreasing. What does it mean that our f prime is positive? It means that our f is going to be increasing, going up. Okay, so we now have some conclusions that we can make. So this is a really important part of these questions, is writing out our conclusions and justifying them. All right, so the first conclusion that I can make is the interval of where it is decreasing. So we can say f of x is decreasing over the interval negative infinity to 3. And why can we say that? Well, we can say that it is decreasing because of what was happening on the top there. Because f prime of x was less than 0, was negative. Okay, we can also conclude that f of x is increasing over the interval 3 to infinity. And the reason we can conclude that was because f prime of x was greater than 0 there. Okay, the last thing we can conclude is actually, so we did our intervals of increase and decrease. The last thing we're going to conclude is if we had any relative extrema. So did we have any relative mins and max? And the way we're going to figure that out is just kind of look at your arrows. What do you notice? Here I was going down, and then I must go up. So that must tell me that my critical value of 3 is in fact a relative minimum. Okay, so I could say f of x has a relative min at x equals 3. And why? Well, because f prime of x changed from negative to positive. Okay, so that's how I know. So all I'm doing is interpreting this number line and making my conclusions. Okay, taking a look at our second function here, f of x equals x to the fourth minus 8x squared plus 1. Same process. First thing we need to do is find those critical values, and in order to do that, we have to evaluate the derivative. So that's 4x cubed minus 16x. We're going to go ahead and set that equal to 0. Okay, so hopefully we recognize here that we could factor out a 4x, and we're left with x squared minus 4. A lot of algebra here. All right, we're going to t-chart, so 4x equals 0. So on this side we would just get x to equal 0, and on this side we have x squared equals 4, so x would equal positive and negative 2. All right, so we have 3 critical values. So when we set up our number line, we want to make sure we put all 3 of those on there, negative 2, 0, and 2, and they are all because we set that derivative equal to 0. Those are all zeros, they're not undefined, okay? And again, we want to label the bottom as f and the top as f prime. All right, so now we're doing our tests. Okay, so we need to test values, and remember we're testing them into f prime. And the thing I want to encourage you to do is use the factored form when we test. It's going to make it a lot easier. All right, so we're going to start by testing, let's say, negative 3. Okay, so if I test negative 3 into this, all right, 4 times negative 3 would be a negative. Negative 3 squared would be 9 minus 4 is a positive. So a negative times a positive is going to be negative here. All right, so you see how I do that? I can kind of put it in there, and it usually makes it go quicker. All right, between 0 and negative 2, I'm just going to go ahead and pick negative 1. So negative 4 times negative 1 is going to be negative. Negative 1 squared is 1 minus 4 is another negative. Negative times a negative is positive. All right, now I'm going to choose 1. 4 times 1 is positive. 1 squared is 1 minus 4 is a negative. Positive times a negative is a negative. Okay, pick a 3. That's going to be a positive times a 3 squared minus 4 is 5. That's another positive. So we end up with a positive. All right, so what does that tell us about the graph of f? Well, where the derivative is negative, we're decreasing. Where the derivative is positive, we're increasing, decreasing, increasing. Okay, so from that, we're able to go ahead and make our conclusions about the graph of f. Okay, so the intervals of increase and decrease. So we can say f is increasing when? Well, it's increasing from negative 2 to 0, and it's increasing from 2 to infinity. And why is it increasing there? Because f prime of x is greater than 0, is positive. Okay, f is decreasing. And where is it decreasing? From negative infinity up until negative 2. You can use the union symbol if we want. Union with or in conjunction with. It's also decreasing from 0 to 2. And why? Because f prime of x is less than 0. Okay? The last thing we want to do is state our relative extrema, our relative mins and maxes. So if we look at this, and we can kind of actually, feel free to draw it in so you can kind of have an understanding of what you're looking at here. So you can see here that we're going to go down and then up and then down and then up. All right, that's the graph of f. That's what it's telling us. Obviously, we don't know our heights and the peaks and how high and how low, but you have this idea that it's going to go down to a minimum relative min at what value? Negative 2. So this tells us we're going to have a relative min at x equals negative 2 and also 2. Okay? And why are those relative mins at negative 2 and 2? Because f prime of x changes from negative to positive. Okay? Then we're also going to have a relative max at x equals 0 because f prime of x changes from negative to positive. Okay, we're going to jump right into the third one here. First thing we need to do is go ahead and find our critical values by setting our derivative equal to 0. Okay, so we're going to go ahead and take the derivative, 2x minus 3 squared times the derivative of the inside, which is 2. So f prime of x here is just equal to 2x minus 3 squared. Okay, oops, f prime of x, sorry. Okay, so we're going to set that equal to 0. And if we did, then we would t-chart this, the left-hand side here, that 6 obviously does not equal 0, so that's gone. And then 2x minus 3 squared, well, it doesn't matter if it's squared or to the 5th or just to the 1, okay? Wherever that is 0, 0 squared is still 0. So we just have to take the inside and set that equal, so we get x equals 3/2. Okay, so we have just one critical value. All right, so we're going to go ahead and make our number line with that critical value, 3/2. Okay, f is the bottom, f prime is the top. Okay, so we are going to go ahead and test a number to the left, but let's take a look at what our derivative function is. If you look at our derivative function here, okay, it's 6 times something squared. What do we know about a squared? What is that going to happen? Whether or not what's in the parentheses is positive or negative, when you square it, it's going to be positive. And then you multiply that times positive 6. We really don't have to do any testing because we should be able to recognize that because this is squared and this is a positive 6, it's going to be a positive times a positive. So everywhere on here, we're going to have positives. Of course, our 0 at 3/2. And so what does that tell us? Well, it tells us that we are going to be, f is going to be increasing and then increasing some more. Okay, so that tells us that we will not have any relative mins or maxes. Okay, because it never goes from increasing to decreasing or decreasing to increasing. It never goes from positive, negative, negative to positive. So therefore, we are going to say that it's increasing, and we can tell that, the interval of increase. So we can say f is increasing, and the intervals would be negative infinity up until 3/2, union with 3/2 up until infinity. And y, f prime of x, is greater than 0. Okay, but that's all we can conclude. There is no relative min or relative max because there is no change from f prime from positive to negative or negative to positive. Okay, our fourth example here, f of x equals x to the 4/3 minus 4x to the 1/3. So I'm going to jump right in and take the derivative. So it would be 4/3 x to the 4/3 minus 1 or 3/3 would be 1/3. Okay, minus 1/3 times 4 would be 4/3 x to the negative 2/3. All right, so this is our, we're going to go ahead and set that equal to 0 here. And as I do that, I'm going to go ahead and factor that left-hand side. So if I'm looking at this, okay, again, it's looking at what's the same on the left-hand and on the right-hand side. So I can see, of course, that I could pull out a 4/3. And then between those two exponents, I'd want to pull out the x to the smaller exponent, the negative 2/3. And so what I'm left with here, well, the 4/3 cancel in this first term. And x to the negative, or I'm sorry, x to the 1/3, divide out and x to the negative 2/3, what would happen would be I would end up with just x. And then minus, these match exactly. Okay, this term here and this term here match exactly, so it's just minus 1. Okay, so I need to clean this up because I need to see, as soon as I see that negative 2/3, that tells me I'm going to have an x in the denominator. And that tells me that I'm not just looking at zeros any longer, but I'm also looking at the undefined values, okay? So we're going to have a fraction bar here. And on the top of that, I'm going to have my 4 and that x minus 1. And on the bottom, I'm going to have the 3, and I'll have my x to the 2/3. Okay, so remember, what we are doing here is we are looking not only for the times when the derivative is 0, but we're also looking for the undefined. So I have two different things that I need to take care of here. I need to set my numerator equal. So my numerator here would be for the zeros. 4x minus 1 equals 0, so x equals 1. And I also, for the undefined, need to set my denominator, 3x to the 2/3 equals 0, so x is equal to 0. So when x is 1 and when x is 0 are my two critical values. Okay, so setting up my number line, I'm going to have those two critical points, one at 0 and one at 1. Now the way I'm going to kind of label these up above the 0 and the 1, above the 1 I'm going to go ahead and put my 0, but above the 0 I'm going to put this symbol which means that it doesn't exist or it's undefined at that value. Alright, so again, f is down here and f prime up here. Alright, and so now I got to test my values. So I'm going to first of all go ahead and test a -1. So -1 into this right here. Alright, so on the numerator I would have -1 minus 1 would be -2 times 4 would be a negative, okay, over -1 to the 2/3. Well, the cubed root of -1 squared is going to end up being positive, so that is a positive. So negative divided by positive is a negative value there. All right, then I can go ahead and test a value between 0 and 1. So I'm going to go ahead and test 1/2. All right, half minus 1 in the numerator would be -1/2 times 4 is still negative. Remember, we don't care the value, just if it's positive or negative. 1/2, it doesn't matter, 1/2 to the 2/3. Well, if it's a positive number to the 2/3, it's going to stay positive. And so that is positive here, so it's going to be another negative there. All right, then I'll test a 2. All right, so 2 minus 1 is positive over 2 to the 2/3 would be positive. So positive divided by positive is a positive there. All right, so what our conclusions are is where f prime is negative, we know that f was going down, decreasing. So we have two places where we see the down arrow, and then where f prime is positive, we're going to go up and we're going to be increasing. Okay, we're able to write some conclusions now. Right now I'd like you to pause the video, write your conclusions. What would you say has happened here to the graph of f? Where are the intervals of increase, decrease, and are there any relative mins and maxes? And then come back to me and see if we have the same answers. Okay, so I concluded that the intervals of decrease would be -∞ to 0 and 0 to 1 because f prime is less than 0. I concluded that the function was increasing from 1 to infinity because that's where f prime was positive, and that there's one relative min, and that is at x equals 1 because that's where the graph is going from changing from f prime changes from negative to positive. Okay, we're going to wrap it up. But I would just really encourage you to make sure that when you come into class next time, that you know the 4 steps for finding our relative extrema and intervals of increase and decrease, the first derivative test, okay? That you know how to find the critical values, to set up your number line, to test values into f prime, to determine the positive and negative, the increase, decrease, and then to make your conclusions, appropriate conclusions and justifications. All right, thanks so much. We'll see you next time.